Every point on a cost curve has a slope, and every slope has an economic meaning. In this lesson, we uncover how derivatives explain the falling and rising sections of average variable cost and average total cost, and why marginal cost must reach its minimum before either of them. Get ready for a complete, mathematically clear guide to cost curves. Let's begin with the simplest building block of all cost curves, fixed cost. Fixed cost is the cost a firm must pay even if it produces nothing. It does not change with output. Think of machinery, rent, or long-term capital commitments. These costs exist whether the firm produces 0 units or 1,000. In our numerical example, we assume total fixed cost of 100 units of currency. Average fixed cost, or AFC, is simply the total fixed cost divided by the output level Q. It is total fixed cost over Q. This gives us the curve, AFC, equals 100 divided by Q. Output is measured along the horizontal axis. As output increases, this curve falls continuously. Why? Because the fixed cost is being spread over more and more units. The slope of this curve comes from taking the derivative of TFC over Q. That derivative is minus total fixed cost divided by Q square. In our numerical example, the slope is minus 100 over Q square. So, AFC is always falling. And the slope becomes flatter in absolute value as output increases, because the fraction becomes smaller and smaller. Now let's analyze variable cost. Variable cost is the cost that changes with output. It arises from the use of inputs like labor, raw materials, and energy. As production increases, these costs increase as well. Total variable cost is equal to output multiplied by the unit variable cost, also called average variable cost. Equivalently, average variable cost is total variable cost divided by total output. Now, look at this quadratic form of average variable cost. We'll use this function for our numerical example and to draw the graph in Mathematica. This curve shows average variable cost on the vertical axis and output on the horizontal axis. The slope of this curve is given by the derivative of the AVC function. Mathematica calculates this derivative as minus 1.5 plus 0.1 times Q. Notice that the slope changes at every output level. This means the AVC curve is not linear, it bends. To find the minimum of average variable cost, we set the derivative equal to 0. Solving this condition shows that the minimum, AVC, is 30 units of currency, and it occurs at an output level of 15 units. This minimum point is marked by the red dot on the graph.
Total cost is the sum of fixed cost and variable cost. When we divide total cost by output, we obtain average total cost, or ATC. So, average total cost is simply the sum of average fixed cost and average variable cost. The derivative of total cost is called marginal cost. Marginal cost measures the cost of producing one additional unit of output. Now take a careful look at the specific numerical forms of these functions that we enter into Mathematica. These formulas will be used for our numerical examples and for drawing the graphs. This curve shows average total cost on the vertical axis and output on the horizontal axis. The slope of this curve is determined by taking the derivative of the ATC function. That derivative is displayed here as the Mathematica output. Once again, notice that the slope changes at every output level. Just like average variable cost, average total cost is a curved function, not a straight line. To find the minimum of average total cost, we set this derivative equal to 0. Solving this condition shows that the minimum, ATC, occurs at an output level of approximately 18.06 units, and the minimum value of ATC is about 36 units of currency. This minimum point is marked by the blue dot on the graph. Similarly, we can find the minimum of marginal cost and the corresponding output level, as shown by the following Mathematica input and output cells. The Cartesian coordinates of this point are 10 and 26.25. This point is shown by the brown dot on the marginal cost curve. Now let's turn to the key relationships among the four cost curves, all drawn together in a single diagram. First, we will identify these relationships. Then, we will explain the mathematical reasoning behind them. Pay close attention to the different portions of the curves, especially where we draw rectangles, to visualize these relationships clearly. Before average total cost reaches its minimum, marginal cost must lie below average total cost. At the exact output level where average total cost reaches its minimum, marginal cost intersects average total cost. Beyond that minimum, marginal cost lies above average total cost. Average variable cost is minimized at the output level where its derivative, or slope, is equal to 0. At that same output level, marginal cost is equal to average variable cost. Similarly, average total cost is minimized where its derivative, or slope, is equal to 0. At this point, marginal cost is equal to average total cost. So both average variable cost and average total cost satisfy the same general rule. The marginal cost curve intersects each average cost curve at that curve's minimum.
As shown by the red dashed lines in this diagram, the vertical distance between average total cost and average variable cost at any output level is equal to average fixed cost at that same output. Using Mathematica, these vertical distances are calculated as 20 units of currency at output level 5, 6.67 units at output level 15, 4 units at output level 25, 3.33 units at output level 30. Each value exactly equals average fixed cost at the corresponding output level. So at any quantity of output, the vertical gap between ATC and AVC is equal to AFC. Now let's go one step further. Over any output interval, the area between average total cost and average variable cost is equal to the area under the average fixed cost curve over the same interval. Between output levels 5 and 30, the area between ATC and AVC, shown by the blue shaded region, is approximately 179.18 square units of currency. This is exactly equal to the purple shaded area under the AFC curve. These results are formally confirmed by the Mathematica integration input and output cells shown on screen. Now, let's explain the mathematical reasoning behind the core relationships among cost curves. We begin with the definition of average total cost. Average total cost is equal to total cost divided by total output. To find the slope of average total cost, we apply the quotient rule of calculus. Next, we make two key substitutions. First, the derivative of total cost is marginal cost. Second, Total cost itself can be written as output multiplied by average total cost. After simplifying, the slope of average total cost becomes equal to the ratio of the difference between marginal cost and average total cost to the level of output. Because the output level is always positive, the sign of the slope of average total cost is determined entirely by the sign of the numerator. This immediately establishes the core relationship between marginal cost and average total cost. When marginal cost is below average total cost is falling. When marginal cost is equal to average total cost is at its minimum. When marginal cost is above average total cost is rising. This is the central algebraic reason why the marginal cost curve intersects the average total cost curve exactly at average total cost's minimum. To establish the remaining relationships, write total cost as the sum of total fixed cost and total variable cost. Next, express total variable cost as output multiplied by average variable cost. Now divide this expression for total cost by output. This gives average total cost equals total fixed cost divided by output plus average variable cost. In other words, average total cost is equal to average fixed cost plus average variable cost. To find the slope of average total cost this time, instead of using the quotient rule, we take the derivative of the two terms in the sum. The slope of average total cost is therefore equal to the derivative of average variable cost minus the ratio of total fixed cost to the square of output. The second term is the derivative of average fixed cost. Because this term is negative for all output levels, average fixed cost is always decreasing, and its slope becomes flatter in absolute value as output increases. The first term, the slope of average variable cost, is negative at low levels of output, and becomes positive after average variable cost reaches its minimum. Because the slope of average fixed cost is negative, average total cost can continue to fall, even after average variable cost begins to rise. Average total cost reaches its minimum only when the rising average variable cost exactly offsets the falling average fixed cost. So every rise, fall, and turning point in cost curves is not accidental, it follows directly from algebra and calculus.